Welcome, everyone. It is my great pleasure to introduce Dr. Sharan Majumdar. He is Professor of Atmospheric Sciences and former Associate Dean of Graduate Studies at the Rosenstiel School. He is also currently the interim co-director of the new Climate Resilience Academy. He has been at faculty for 20 years, and he and his collaborators investigate tropical cyclone formation and intensification. This involves sensitivity diagnostics, ensemble prediction, evaluation, satellite and aircraft observations, data assimilation, risk communication. He teaches courses on this and several other topics, weather forecasting, hurricanes, predictability, tropical meteorology, etc. He's going to now talk about hurricane prediction and resilience challenges. Thank you very much, Dr. Majumdar. The floor is yours.
Hey, great. Thank you very much, Prannoy, for graciously inviting me to give this seminar and for the kind introduction. So the seminar is fairly timely given Hurricane Ian that made its landfall in Florida and South Carolina and Cuba last week. So first, I'd like to acknowledge my funding agencies through which a lot of this work was done, NSF, NOAA, NASA, and the Office of Naval Research, and also all of my research group members. I won't have time to present all of their work, but they're doing a lot of interesting stuff on the topics that Prannoy had mentioned. Our ULink team, some of that work will come up, and collaborators and friends all around the world. So the seminar is divided into three phases. So the first phase will discuss a bit about Hurricane Ian, the impacts and some of the resilience challenges that Ian really sort of brought to bear, that we keep getting these reminders every time there's a significant landfall. Then we'll go into a little bit more sort of class mode and talk about some basics of hurricane structure and the tools that we're using to predict hurricanes. And then finally, we'll talk about a little bit of research that I did on my sabbatical at the European Centre for Medium Range Weather Forecasts, where we're evaluating an in-house high-resolution version of the European model. So we will start with a fairly grim slide here. So this shows the deaths that are attributable to Atlantic tropical cyclones that are divided into the type of impact. And it shows that by far the largest killer is the storm surge. That's 49% of all the deaths can be attributed to storm surge. And unfortunately, storms such as Ian are going to add to those numbers too. The rain actually surprised me when I saw this. It's a paper that's published by a former deputy director of the National Hurricane Center. And they found that about a quarter of deaths are from rain, and much of that is inland flooding. Then we see some of the other sources, wind and tornadoes, for example, accounts for about 11%. There's a lot of focus on the wind when we talk about the category of the hurricane, but we need to be thinking about other impact-related metrics beyond the category so that the public and decision makers are better aware of those types of impacts and where and when and how severe they might be. So for Hurricane Ian and for all hurricanes, the National Hurricane Center provides 6 hourly forecasts. And in addition to the regular forecasts, they provide a series of key messages. And this was produced over 2 days before the landfall of Hurricane Ian over Florida. It hadn't actually made landfall over Cuba at the point that this advisory and key messages were issued. And so this is where they write in more plain English about the impacts that are anticipated in different regions. And so the first key message is about Western Cuba, where it's also mountainous terrain and there are potential issues with mudslides in addition to several other threats. If we go to number 2 to 4, that these are now more oriented towards the Florida coastline. And so it was pointed out over 2 days in advance that there'd be life-threatening storm surge. That was possible along much of the Florida west coast. And the highest risk is from Fort Myers to the Tampa Bay region. And so that was publicly communicated at least 2 days in advance. And there was the emphasis on the local officials providing advice to the residents. Then the other impacts that were identified in advance were the hurricane force winds, which are especially in the eye wall, and we'll talk about the hurricane structure as we go through the talk. And then also heavy rainfall, as we pointed out on the previous slide, that rainfall is a very important threat that needs to be recognized. On the right-hand side, so the Hurricane Center usually provide 2 of their priority graphics out of their whole suite. So in the top right-hand corner, it gives the cone of uncertainty that is fairly well known. And that gives essentially areas in which there's a 2/3 probability that the track will lie inside. And so we'll discuss that a little bit more. And then on the bottom panel, it shows the most likely arrival time of tropical storm force winds. So this is done in terms of a probability, which is in the colors here. And then a timing is given in these lines here. And so this is useful for preparation, that one should be prepared and have put their shutters up and made all other preparations before the onset of tropical storm force winds. It's not a good idea to put shutters up when there's 40 mph and more winds blowing. So the cone of uncertainty has received a lot of attention in the last week and over the last 20 years. And I noticed just prior to Hurricane Ian's landfall that it was spoken about on TV as a cone of concern, which is actually concerning because the cone is designed such that 1/3 of all of the track forecasts are expected to fall outside the cone. And so it's not to say that if one's outside the cone that one should not be concerned, that there's a continuous concern because there is a probability that the center may be outside that. And then moreover, the hurricane is not just one point either. And so this has been emphasized for decades, not to follow the skinny black line on the track forecast, that the impacts from storm surges, wind and rain can be many miles away. And so as you might expect, this has been a very active topic in the media. And there was an article in the Washington Post 3 days ago that you can take a look at about some of the confusion in the hurricane cone. And one of my research group members and one of our collaborators is quoted in the Washington Post. And they also gave a link to an article that just got published in the Bulletin of the American Meteorological Society that was part of our ULink project from a couple of years ago. And so there we evaluated the public comprehension of the cone of uncertainty graphic. And we found a few concerns that, for example, about 40% of the respondents thought that impacts are not likely to occur outside the cone, for example. That's a fairly short article, and I definitely recommend in the context of Ian that it's worth a read. So there are many types of forecasts that are now being made that are tailored more towards the impacts. So the National Hurricane Center has a suite of storm surge forecasts, and now they make watches and warnings. And this was really sparked by Hurricane Katrina in 2005, then Hurricane Ike in 2008. And so here's an experimental forecast. It's up there on their website. And this was issued 2 days prior to the landfall of Ian on the Florida coastline. And we see some fairly large numbers here for storm surge, 4 to 10 feet in this orange through Red Street, which is a fairly long stretch of coastline. And it does include the Fort Myers area. And there were surges that are predicted even further south there. And so it's fairly well communicated that these surges were expected along the coastline. But there is a bit of a communication issue with even just the phrase storm surge. In our own public surveys and design charrettes, we've found that many of the respondents are not aware of the terminology of storm surge. Another graphic just to show the sheer size of a hurricane is a satellite image here. And so this shows the eye of the hurricane, which is sort of clearing out a little bit here. And then the outside of it is the eye wall. And then we see some rain bands amongst the central dense overcast here. And so the high winds generally in this area that I'm moving my mouse, with the highest winds in the eye wall here with a radius of about the 30 miles or so. So we see that large areas can be impacted quite dramatically by the hurricane. The winds are coming onshore on this side, and they're also pushing the water that's creating the storm surge to the south of the landfall location. So this is all to say that hurricanes have a large impact over a fairly broad area. And this is exacerbated here or exemplified by this graphic, which shows now this stretch of the Florida coastline that was most inundated, with many buildings being affected in the Cape Coral and Fort Myers area, especially right at the coastline due to the storm surge. And then also far down to Naples and Marco Island, where there's still surveys to assess the actual height of the storm surge, but at least at the time of publication of this in the Washington Post, that there are at least 6 feet of storm surge flooding that had been observed in parts of Naples. So this all speaks to a need for resilience to hurricane impacts in many different ways. So there's a long-term resilience question here. And so that then brings in a lot of questions about infrastructure that many in your departments are investigating. And so that involves buildings that can withstand storm surges, wind damage and flooding. Also, as some of you are working on, is ways to sort of dissipate storm surges through corals and through some manufacturing of artificial sort of reef-like structures, for example. And so those are all long-term projects, and working with local authorities, bringing in federal and state funding to then try and scale up these types of initiatives that are being developed at and other places. Other aspects, including improved evacuation routes. It is a big transportation problem here in this part of Florida. And then also, the National Hurricane Center emphasizes this, improved training and education. Then there's also resilience that's needed in many different ways on the event-by-event basis. And so this is more what I work on, which involves much of the meteorology. And so this includes an understanding that forecasts are never going to be perfect, but we need to keep on improving them. In this context, we need to be able to communicate forecasts better and make sure that our respondents, our officials, understand the uncertainty that comes with the forecast, the level of confidence in these forecasts. And we hope that that will then lead to improved decision-making by officials and residents on a case-by-case basis. So all of these are intertwined. Just one point here on building codes in Florida and the other states. So as many of you know, that the Miami area was hit by Hurricane Andrew in 1992, and that was a wake-up call. And the state of Florida started to develop and implement much more stringent building codes after 1992. And then Florida was crisscrossed by 4 hurricanes. I actually had enough of it in October 2004 and evacuated out to California so I could keep working. But we were under hurricane warnings quite regularly back in 2004. And those impacts then led to a further tightening of the building codes. So buildings that are built in the 2000s are generally built to a much higher standard. And then especially in South Florida, the buildings are really built to a good code largely, even compared with the rest of the state. There's this nonprofit institute, the IBHS, and they rate the states in terms of their building codes, both statewide and by local jurisdictions. And so it shows up here, and I was sort of pleasantly surprised by this, that Florida is definitely on the positive side. It's very highly rated in its building codes, and it has been over the last few years. We see that the Carolinas and Virginia are pretty good, but then other states such as Texas, for example, and Mississippi and Alabama are less so, that some states don't even have statewide building codes. So there's definitely a disparity in the building resilience across the different states. On the topic of Texas, that here's an initiative that one of my friends, a former director of the National Hurricane Center, Bill Reed, is involved in. And this is part of a project that's called the Ike Dike. And it's a proposed coastal spine that is to be built across Galveston Island. And the goal there is that for surges, even as high potentially as 12 to 15 feet, that it doesn't push large volumes of water into the Galveston Bay Area. That there's a lot of residents and a lot of petrochemical industries around there. And so this is all sort of in the planning and design phase. It's not in the implementation phase. The local governments, the local universities, and the many collaborators around the country, together with the local petrochemical industries, are sort of working on planning for this coastal spine to be built in the shipping channel. Just wrapping up the resilience part of this, that there are multiple other challenges. So in addition to thinking about better ways for evacuation, one also needs to think about sort of the short-term end goal, that there need to be places to evacuate too. There also needs to be available gasoline and food, both before, during, and also after the impact. That sometimes the aftermath is not quite planned for. It's more so sort of the lead up to the impact. There are many public health consequences, of course, and several of our medical campus folks are working on aspects such as building better structures or better understanding of and policies of evacuation of hospital patients, especially those, for example, who are on dialysis machines or undergoing chemotherapy. That it's just a very, very sensitive problem, and yet we have uncertainties in all of our forecasts of the intensity and where the hurricane will go. Another public health concern is that more people are admitted to hospital after the impact through breathing difficulties, through ingestion of chemicals that are released through damage of buildings, for example. There are also other aspects such as potential for more vector-borne diseases, for example. Then in addition to this, there's also the legal and financial challenges that insurance and reinsurance industries pay a lot of attention to climate change and also hurricane impacts on an individual basis. And there are legal questions also about a particular damage or roof being damaged, for example, that is that attributable, for example, to a hurricane. So there's a lot of gray areas there that come up in the questioning. Okay, on to the prediction side. So this is sort of beginning more so phase 2 now. So we work very closely with the National Hurricane Center, and they are as you all know, so the main national agency that issues forecasts, watches, and warnings. They used to be based at that they were in the Unger building, so not too far from the engineering building there. And then they are also across the road at US 1 at the time that Hurricane Andrew hit in 1992. Now they're on the FIU campus in a very heavily fortified building here. They issue 6 hourly forecasts in the Atlantic and the Eastern North Pacific. There's a storm out there right now in the Caribbean. And they predict the track, the intensity, also the size of the hurricane through wind radii. And also, as we pointed out earlier, the storm surge, the potential heights, and then they issue storm surge watches and warnings. Another NOAA Center issues rainfall forecasts, and the Hurricane Center links to those. And then the local National Weather Service offices around the country also provide some forecasts of impacts. And these are actually my favorite products, and I'll show those on the next slide. And then also the last bullet there is just to say that all of these forecasts reliant on the forecast models, which is what we're going to discuss over the next few minutes. But before we jump into the models, that we want to talk a little bit about the impact products and then talk a bit about hurricane structure and some of the fluid dynamics. So this is an example of the impact products. Our local weather service office produces these. They're the brainchild of Pablo Santos, who is the meteorologist in charge of the National Weather Service Miami office. And these graphics show the threats and impacts for wind, flooding, rain, storm surge, and tornadoes. They have different color scales for the severity, although they're uniform across each of the different threats. And there's some plain language descriptions here about the types of damage that might occur. These are not widely broadcast, though I do see now that the TV channels are starting to adopt more of these impact-related type graphics. So following our ULink project, that we have a NOAA grant where we're working with the Weather Service and the National Hurricane Center to identify whether we can improve upon these graphics and build more of a time dimension into these graphics, and bring the public in to hear their critiques and suggestions for redesign. So that's part of some ongoing research across different schools at UM. Okay, into some meteorology here. So here's the definition of a tropical cyclone, of which the hurricanes are a more intense version of. So there are a lot of different words here that the National Hurricane Center has to evaluate in their description of whether a particular storm qualifies as a tropical cyclone. So it has a warm core, meaning the local temperature is warmer than the environmental temperature. It doesn't have fronts associated with it. Its scales are of orders sort of hundreds of kilometers or so. It originates over tropical or subtropical waters. It has clouds that are deep and organized, and this is very subjective here. And then there's a closed surface wind circulation about a well-defined center. So that's quite a mouthful there, that all of our students in meteorology have to be able to define this in their exams. And so here's a sketch of an anatomy of a tropical cyclone. It's not to scale. That the height of this is about 17 kilometers or so, and the breadth of this is order hundreds of kilometers through to the outer rain bands and the outermost clouds. What we see here is that we have an eye of the hurricane, and we have some slowly subsiding air here, which can clear out some of the clouds in the most intense hurricanes. Then we have the eye wall, which brings most of the wind damage. And so the eye wall is here of order sort of tens of kilometers from the center of the eye. And so we have these really intense winds that rotate counterclockwise in the northern hemisphere. And we have strong updrafts with the eye as well. We then have outer rain bands. We have updrafts associated with those and some downdrafts. And so we have this sort of fairly complex sort of wind type circulation. But the eye wall is very important. The rain bands are very important. We have air that is spiraling in the boundary layer. Now, the boundary layer is the layer which we live in, and it extends up to about a kilometer or so in the hurricane. So that's here we live and breathe. It's very influenced by the ocean. So air-sea interaction is a very important aspect of the hurricane. And professors such as Brian House and many others work on the air-sea interaction aspects of it. And then at the top of the hurricane, there's the outflow layer. And so the outflow is kind of like the exhaust of a hurricane, that one can think of a hurricane as a heat engine. It has a warm core, and it's really through warming, through condensation of water vapor into liquid water, that we then get this warm core. The warm core then affects the winds, and it serves to strengthen the winds as one goes down in the hurricane. And we get the strongest winds, as we'll see in a bit, near the bottom of the hurricane. And so one can think of the hurricane as kind of this heat engine where we have energy that's being driven from the air-sea interaction, the condensation or warming, and then it needs an exhaust. And so the outflow serves as this exhaust that carries much of the air away from the hurricane. And that's what you see on the satellite pictures of the hurricane. It's very much this cirrus outflow. Here's some eye candy, literally. It's a picture that one of my colleagues took from a Hurricane Hunter flight. And we see that the eye is fairly clear where the aircraft is, and that the eye wall actually slopes outwards. So it's like a sort of football stadium type effect here in the eye. Looking at more of a schematic here, we're looking at the radius from the center of the eye, and we're looking at the height. And the circulation fluid dynamically can be broken into a primary circulation and a secondary circulation. The primary circulation here shows that the wind speeds are largest at about 1 kilometer altitude here in this schematic. And the highest winds at every level, that they sort of flare outwards with height here along this radius of maximum winds. Below this 1 kilometer, we have the boundary layer here, and the winds are a bit less strong there. The Hurricane Hunter aircraft generally fly between about a 3 and 5 kilometer altitude here, so they're not flying in the most dangerous winds here. There's actually a mathematical formula here that I'm not showing, I'm just showing the general force balances that are important. And this actually explains much of the flow in a hurricane. And so we have a low pressure system here that's a hurricane. Then generally in fluid dynamics, air flows from high pressure to low pressure. And this is called a pressure gradient force. However, this is not the only force, that we have flow that is moving around the low pressure system, and by virtue of its curvature motion, that there are two other apparent forces that are in the frame of reference of the blob of air that's moving around the hurricane. And those are the centrifugal force and the Coriolis force. So this one is by virtue of the rotation of the Earth. And these three forces actually balance each other out above the boundary layer and below the outflow layer, which then creates this force this balance called gradient wind balance. And we then get this sort of steady state motion around the hurricane here. However, in the boundary layer, we also have friction. And so what does friction do? Friction slows down the motion. These two forces related to the velocity. And so if we have a slower motion, then these forces get weakened, the pressure gradient force starts to dominate. And that's why we have flow that slightly spirals in towards the hurricane nearer the surface here, like we mentioned a bit earlier, and we'll mention in the future. We also have a secondary circulation, and this is the in, up, and out. So now this is the radial component of the wind on the same type of chart here. So we have the eye here at 0 radius, and we're going out about 180 kilometers. Then we're going upwards here, 17 kilometers up in the atmosphere. So we have inflow here. That negative means that we've got an inward radial component. So this is bringing in energy and momentum into the center of the hurricane. We have upward motion in the eye wall especially, and then we have this outflow here that's carrying out some of this air. We also have this little bit of sinking motion in the eye as well that can clear out the clouds. So there you have like much of the basic description of a mature hurricane and the flows inside one. Now, if we get more complicated here, that we have these full fluid dynamical equations for motion that are scaled for the atmosphere. And the atmosphere really has many different scales, from like the scales of the planetary motions across the Earth, right to the scales of the small clouds that we see even just over Miami or over the campus. And so we need to account for all of these scales because they're all important in hurricanes. We have 4 basic conservation laws. So we have conservation of momentum, and then I've annotated some of the terms here that we're now a bit more familiar with. And so this tells us just how our winds are going to change based on all of these different forcings here, and includes friction and other things too. Then we have the thermodynamic conservation of energy here. Then we have the conservation of mass, and we have the conservation of moisture. And this is quite complicated because we also have different types of physics in a hurricane. That we have ice in a hurricane, so above the freezing level, or we have supercooled water, we have hail, and we have also this sort of hybrid of sort of ice and water called grapple. And so those species are also important for intensity change, yet they're very hard to measure. And it's also dangerous to fly the aircraft above the freezing levels too. Then we also have the first law of thermodynamics here too. So these all go into some of the world's biggest supercomputers to then crunch out our computer model outputs of track and intensity and so on. We have 2 different types of computer models. We have global models, and as the name suggests, these models integrate those equations on a previous slide across the entire globe. And so the atmosphere here is divided into these grid points here. At the ECMWF, the European Centre, where I'm a visiting scientist, and I did my sabbatical, that these are about 9 kilometers across effectively. And then there are 137 of these vertical levels here. And so each of these grid points needs to be able to talk to each other horizontally and vertically in solving the equations of motion. And they also need to be able to handle these different physical processes. Ideally, one would be able to handle the solar radiation, that's visible radiation, and then also the infrared radiation from the Earth and in the clouds in each of these grid points. And also various other physical processes, such as the individual clouds and the air-sea exchange processes. However, in global models, they can't really be explicitly resolved to this level of fidelity. So one needs to do what's called a parameterization, which is a kind of approximation for representing like clouds in a particular grid point here. And so that's a shortcoming of global models, that they also don't represent eye wall structures very well. And hurricane intensity, which is the maximum wind speed, that's almost always in the eye wall itself. So if we can't replicate the eye wall well, then we can't make a good intensity forecast. So to remedy that shortcoming, which is really an aspect of the supercomputing not being able to do this, to integrate those equations at a better resolution than 9 kilometers in real time, that we have these regional models. And so these are like a magnifying glass over the hurricane itself, and they're embedded within the global model. And so here we have models such as the Navy model that I'll speak about, as well as the NOAA's HWRF model, which this is. And this shows these nested grids that follow the track of the hurricane, but they're at a much higher resolution. In this case, it's a 2-kilometer grid. And here you can get these very fine scale eye wall and rain band structures, which the global models do not capture at their current operational resolution. This is just a quick schematic of how the forecast models work. So this runs ad infinitum till the end of time. And so one aspect that I've not really introduced, and I won't, but it's a separate seminar, is about observations in hurricanes. And so this involves satellite observations, aircraft observations, ground-based observations, all being combined with our best estimate of the state of the atmosphere through this process called data assimilation. Now, I used to do a lot of work on data assimilation. I do less now. And this then creates the initial conditions for the model to be integrated forward from. So this can be integrated out to, well, in several weeks in advance, however long we want to integrate them out. Of course, the forecasts get less reliable as we go beyond a few weeks. And then also we use a short range version of this to provide a first guess that we then combine with new observations that have come in the meantime. We assimilate those observations, combine them with the first guess, get a new set of initial conditions, run the model off that. And so we do this ad infinitum on the supercomputers. And this gives us separate series of model forecasts every 6 hours. How are our forecasts doing? Well, the National Hurricane Center synthesizes these models, and then the human makes the forecast that you see on the National Hurricane Center advisories. And this is the evaluation of their track forecasts over the last 31 years. And these are for 1 through 5 day forecasts. So a good sign here is that the track forecasts are by and large improving, that there is some noise sort of year to year, but by and large they're improving because our models are getting better. You know, forecasts are learning more from the models too and how to synthesize them. We have more and better satellites out there. We have more advanced data assimilation schemes that know how to make use of the myriad observation types, and literally about 10 million or so observations that are getting into the model every day. However, the intensity forecasts are a bit more volatile. There has been a lot of investment in the agents by our funding agencies, especially NOAA, but also many of the others, in improving our model forecasts of intensity. And we see here that there's been some improvement over the last decade, but it's still not completely clear. There's a lot of volatility season to season. That 2019 was dominated by Hurricane Dorian, and the 4 to 5 day forecast had real struggle with the intensity prediction there. So a lot of our emphasis, a lot of my research group's emphasis is on the prediction of hurricane intensity. Before I move into research, just talk a little bit about ensemble forecasting, that we work on this a lot too. And so this is to think about many forecasts to capture the possible range of scenarios. And one can make quantitative probabilistic estimates using ensemble forecasts. So for example, like what's the probability that downtown Miami may receive hurricane force winds? And that should help inform decision makers based on their sort of risk analysis, that 30% chance worth sort of evacuating people for example. And then also ensemble forecasts can yield a level of confidence in the forecast, that if we have many forecasts that are spread out, then that will suggest a lower level of confidence in a forecast compared with if the ensemble members are all like tightly packed together. And we'll look at these examples now for the ECMWF ensemble for Hurricane Ian. So when this was initialized, this ensemble, that Ian was just a tropical depression. It didn't have the name yet, but already, and this was 2 weeks ago today, that we had some suggestion that there could be some impacts over Florida, including potentially here. That I actually canceled my meetings 2 weeks ago and just went out and bought a whole load of stuff in case of the need for evacuation. And so it's always good to sort of look at the early forecast, just as without needing to panic, just to sort of top up the car with gas before the hype train begins. However, 4 days before, so this was now the Saturday, that the ensemble shifted more towards the left, and there were fewer members looking at Miami here. And then so 3 to 1 day before the landfall, that there was really more of an emphasis on the left. And some of the other models and ensembles were actually further towards the left, and the ECMWF, in this instance, provided a better general idea of the possibilities. That being said, many of the other models have done better than ECMWF for some of the other storms. So it's important to really evaluate these holistically as opposed to on a case-by-case basis. Which actually leads directly into what I did on my sabbatical at ECMWF here, which was in 2020 to 21. Actually, we were in lockdown most of the time, so I was doing this on a couch fairly near ECMWF and then meeting with my colleagues in the pub to discuss ideas. One of our objectives was to really provide some more detailed diagnostics of the modeling sensitivities and then exchange those with the hurricane prediction community. So what we did was we benchmarked the ECMWF in-house experimental forecasts. And so our colleagues did a lot of different runs with different physics. And what I'll show here is different resolution, and then compared it with the US Navy's regional model. So there's difference in philosophies here, that the European Center is a global modeling center, that they care about modeling ice sheets, precipitation and all around the world, southern hemisphere flows, impacts everywhere. So they hold themselves accountable for many different weather types. For the Navy model here, which is called COAMPS-TC, that this model is specifically designed and tuned for tropical cyclones. So what we did was we ran a series of modeling experiments in the ECMWF system, including a 4-kilometer version of the global model. Now, the operational version is 9 kilometers, as we discussed a bit earlier. The COAMPS model that's run operationally, the regional one, that's one that has that magnifying glass. And so that's like a 4-kilometer grid that follows the hurricane. And 2020 ended up being a pretty wild year. I mean, not just for the pandemic, but for hurricanes too. And we went deep into the Greek alphabet here, with storms affecting land even right through to Iota in the middle of November here. So for our science and for evaluation, that we had a very good sample size for statistics here. I won't show the statistics in the interest of time, but we've just submitted a paper that we hope will be published, and I can give the link to that hopefully after it's published. So I'll just show some examples here with the fidelity of a 4-kilometer global model. So this is a horizontal structure at the surface of the wind in the left panel and the rainfall rate in the right panel. The wind here is showing quite a realistic eye wall. So we have the wind barbs here, and then we have the wind speed with a maximum wind speed of 130 knots. For this case, which was Hurricane Laura in 2020, Hurricane Laura made landfall, and it was in Louisiana, and it was a 130-knot hurricane. So I've certainly cherry-picked this. So this is a total showcase that not all the forecasts were this good, but we're very encouraged just to the fidelity of the model in this and other cases in being able to replicate realistic eye wall structures, and hence have some potential for predicting intensity. COAMPS-TC was a little bit on the weaker side here, but it still was a very good prediction. And then here's a comparison of the rainfall rates here, and also the size of the eye we see is a little bit different. But we're just very pleased to see in the 4-kilometer simulations at ECMWF that it's able to simulate an eye wall at all, and then also some representation of the outer rain bands on the right-hand side of the storm. So this provides some encouragement that we can then start to make impact forecasts of rainfall and storm surge and winds, even using the global models. We're not there yet, that this is in-house. We hope that this can be made operational around 2026 or so, when the supercomputing is available to run these in real time. Then this is just quickly the vertical structure. And so we see here, we've got this sort of structure that we also showed in the idealized version earlier in this talk. And then we also have this inflow in the blue, outflow in the red. And then we also have this warm core in the ECMWF in the same way that it's there and it's present, but a bit weaker in the COAMPS TC for this particular storm, which was Hurricane Laura. So we did this over a large number of cases and produced a more quantitative evaluation of these. And we also evaluated the pressure-wind relationship, which, as we saw with gradient wind balance, is an important and quite realistic relationship. We could compare this against a verification here, which are these black dots. And we see that the black line is actually obscured by this purple line. And it shows that the purple line actually did so well here for COAMPS TC that its pressure-wind relationship was very good. With ECMWF, it wasn't quite as good, but EC4 for the higher winds was better than the other versions of ECMWF, except this one, but this had other issues too. So just to conclude, this is just from the ECMWF study here, that the 4-kilometer version was less biased than the 9-kilometer operational ECMWF forecasts. The COAMPS TC was generally better and less biased, so it had some stronger wind speeds and better estimations of the radius and maximum winds than the 4-kilometer ECMWF. But progress was still demonstrated a lot through these numerical experiments for the 4-kilometer resolution, the new physics, and the wave drag, and others too. But it still also told us that we need to parameterize the convection, the clouds, and everything in the global model, that we're not yet ready to explicitly resolve clouds in global models. We also have major concerns with initial conditions for in global models for the very intense hurricanes where you need to resolve the small scales in the eye wall. And if you want to learn more about this, so we have a 130-page report that my close friend and collaborator, Linus Magnusson, led while I was on sabbatical at ECMWF. And this was written for management, and so there's a lot of non-technical aspects here that are worth a read. So it gives a lot more depth to this, and it's also perhaps a good cure for insomnia. So just finally here, wrapping up, we want to resolve hurricanes adequately in models. We also need to develop consistent model physics. We found some substantial concerns with how hurricanes are initialized in the models. So we need to think about how we can initialize at a better resolution with better assimilation of targeted satellite and aircraft observations. And that's a field that I worked on a lot and have written a review article on. And I think it's still quite pertinent that we need to think about how better use these observations from Hurricane Hunter aircraft, for example. The next bullet here, this is ongoing across many of the centers and in research labs, including at UM, in holistically coupling the atmosphere to the ocean, the waves, and the land. We have many scientific challenges here, and this is what 3 of my PhD students work on hurricane formation, and 2 of my PhD students work on rapid intensification. They're very important topics that I haven't really touched on here. What I do want to emphasize, especially here, is the need to develop impact forecasting in models. So we're kind of there in a way that we have rainfall prediction improving, we have wind prediction improving, but we need to start coupling these to storm surge models and provide more precise representations of the wind structure, better representations of the rainfall structure, and also the hydrology. So that's now getting into the river prediction and where rivers may be breaking their banks. So that's been a major issue over the last week with Hurricane Ian in central Florida. And then finally, we can't ignore uncertainty. And so we need to think about better ways to predict the uncertainty. And also on the communication and management side, how to deal with the fact that we have uncertainty that is inevitable. So with that, I'll close and thank you all for your attention, and be glad to take any questions. So thank you.
Thank you very much.